we're going to have a look at using PhreeqCi. So the easiest way to start is just to search for it and then wait for the program to start up. So here's the initial program window that we start to get, and it probably looks a bit daunting at first. So what we will do, of course, is to ease you through it, hopefully. So we're also going to use some of the data from the WIR system for Robertson Park and use it to see if we can make some assumptions about what might be controlling metal concentrations in the water. So the way that we get information in, first of all, we start, as with just about anything, as a solution. So we just to run you through, we've got a whole lot of toolbars. There are various different types of modelling that we can do, including transport modelling and so on, including reactions, by incrementally adding an amount of substance. But we're just going to set up a system with a whole lot of total concentrations and pH and redox potential and things like that, and see where that gets us, and we'll talk you through it as it goes. So what I'm going to do is click on this icon here, which gives us our solution, and it'll basically start us with this dialog box where we can put in some of our starting information. Right, so I am going to start with that. We're going to give it a description. You don't have to do this. This is where the analyses are from, I think. And pH, we'll notice from the information, is 8.1. PE I will leave at 4, which is kind of moderately oxidizing conditions. Temperature on the day of measurement, I think it was 17 degrees. Redox, we'll just fix it at the PE value for now. We can change that if we need to, but I don't think we'll need to. We'll assume that it's a relatively dilute solution, the density of 1, and the water mass. Look, it makes a difference for some applications, but we don't need to worry about that. Well, that sets up the basic properties of the solution. If we click on the individual element tab at the top, we get another dialog where we can select a bunch of things, and this is where we can start to put in our elements here. So we're going to select the ones that we know we have data for. Aluminium, remember this is the totals. The species will be calculated by the program. We have going to set our default database as using the we use the Intec version 4. Okay, so back into solution. So here we have the tab which we click on at the top there for individual element input. At the moment we'll just include the elements that we know that we have. So aluminium, arsenic, cadmium, chromium, iron, magnesium, manganese, molybdenum, ammonium, and this will come up slightly differently in our output, our kind of script window for this, but at the moment it's just ammonium and nitrate. We have data for nickel. I'm going to put in sodium because we've got a measurement of salinity, and in that case I should probably put in chloride, as well. And we have lead, and we have phosphorus, and the last thing we have is zinc. Right. It's not enough just to put them in because we need concentrations. So we're going to put in the concentrations that are on a particular day where we've got complete data. Arsenic 0.001, cadmium actually 0 on that day, chromium 0.003, iron 2.6. Some of these may be overestimates, of course, because we didn't have dissolved measurements for everything. We may just have totals, so on an unfiltered sample, which is slightly problematic, but we can deal with that as we go as well. Magnesium. Okay, I'm actually going to go back and just pop calcium in as well. The reason I put calcium in is because we've got water hardness as well. So we will, and water hardness and calcium carbonate equivalents. Sorry about the mucking around. We'll get this out. So we're just going to give these some nominal values, and I'll explain these as we go. Manganese. Leave that 0. Molybdenum, I'll leave it 0. Nitrate and ammonium. So ammonium 0.026. Nitrate 0.03. Nickel 0.002. We're going to have to not forget to change our units, because the units that we have for concentration in the spreadsheet from WIR are all in milligrams per litre. Sodium 15.7. There's a total salt concentration of, I think, 40 milligrams per litre, so we're just going to apportion that between sodium and chloride based on the atomic masses. 0.004 for lead, phosphate 0.011, zinc 0.016, and calcium 8. Now, let's just fire up Excel and I'll explain why we're using these particular values. So Excel's firing up and behind, and we'll go to where we have some input, and I'll actually make that visible enough for you guys. So I'll just pop that up here and maximize it. Okay, so to explain a couple of things, I'm using the data from the 18th because we have data from both an in situ and grab sample available on that day, and that gives us more information. Okay, so I'll just select all those. Actually select that column as well, so you can compare the values. Okay, so here's our hardness value of 22, and that's as calcium carbonate equivalents. So if I flick back to PhreeqCi, the calcium carbonate equivalents are as 22 milligrams per litre of calcium carbonate. So I'm just guesstimating here that roughly half the mass of calcium carbonate is calcium, and then apportioning that between calcium and magnesium. So 3 for magnesium, 8 for calcium. Look, it it could be different from that, but we don't have any other data, and I'm not sure whether playing around with that would make a lot of difference. Now, the main tweak that I've done is based on our salinity value. So I've got, as I said, total salinity based on the in situ measurement of 40. There's our 17 degrees temperature. And we could also put in dissolved oxygen. We may just pop that in a little bit later on because we've got a milligrams per litre value from that. So salinity of 40. And so what I've done is say that that 40 is made up of sodium and chloride. Because of the relative atomic masses of sodium and chloride, it must be that many milligrams per litre of sodium and that many milligrams per litre of chloride. Okay, so that's how that works, and all the other values are taken directly from that particular day. It could have been another day, but I'm just choosing to use the most recent one for which we have complete data. Alright, and where possible, also, you can see that I've got, say for zinc there, we've got a soluble value and a total value. I've tried to use the soluble value, 0.016 here, wherever possible, but if it's not available, I'll use the total value. Now, as I said, there could be some problems with that, and I also like to set the charge balance, and we're going to make sure that the charge balance is achieved by tweaking the chloride concentration, and hopefully there will be small errors in the charge balance, and it means that chloride concentration, being one of the major ions, won't actually change that much. So we save that. We can see that in the script window of the PhreeqCi, we get those data in a form which can be read by the PhreeqCi program and used for input as well. So that's at this stage all that we need to do. May just pop an N statement there as well, just for completeness, and I would save that somewhere. So I'll save as, and we will put it somewhere. I don't know what to do with it. Put it in here, and we'll say presentation 1, just for argument's sake, and save that. Okay. Now you can see, now that we've got that in there, we have the run button highlighted, so we can run the code that we've just put in. Okay, so our input file is the one that we just saved. It will automatically name the input file, just give it a different extension, and the database file is, I presume, the one that we said it would be, Mintech version 4, so we don't need to change that. And then if we click on start, it will run it, and hopefully run it without errors, which we can check. Okay, it didn't say that we had any errors here. It will tell us where our data come from, tell us how long it says to run and so forth, so we dismiss that. And now PhreeqCi will switch automatically to the output tab. Now there's a lot of information in here, so I'm just going to make it a little bit more visible and just go through the type of information that we, so it's reading in our file, which has a name. We gave it a description, just to verify that we are using the database, and we can check what we've put in. Right. So what it does is that sets up our calculation, our initial solution at least anyway, and then we'll calculate the speciation based on that initial solution. Okay, that's not so interesting for us. Well, I lie. In fact, it hasn't done that, so that's our final calculation. Don't use this enough to not get confused about it. Okay, so iterations 9, there we go. So it has actually solved this solution. So remember, it's creating a whole system of algebraic equations and solving them simultaneously. And so if we look down for each component, or each element as we know it, we'll have it divided up into a whole set of calculated species. So with the total aluminium of this concentration, which looks a little bit different from our input because now it's in molality or moles per kilogram, which with our density of 1 equates to moles per litre instead of milligrams per litre. So don't worry about the apparent discrepancies in the concentration table. It's showing us, first of all, that most of the aluminium at pH 8.1 is present in hydroxy complexes, in particular the AlOH4 species, but some lower order hydroxy complexes as well, these ones here, and very minor amount as free aluminium ions, and we can go through every single possible element and see how it is speciated in that environment. Okay, now the next thing PhreeqCi will do is whether we specify that solids exist or not, and so far we haven't specified that solids exist. It will calculate saturation indices for us, so that we're looking at the first column here, the one headed SI. Now these are actually log SI values, so anything that's negative, the solution is theoretically undersaturated with respect to, but look at this one here. Boehmite, so a crystalline aluminium oxyhydroxide, has a positive value, and in theory at least the system should be able to precipitate boehmite, and that may be part of the issue with having only a total aluminium value in there. Just check our spreadsheet. Actually, we do have a soluble aluminium value of 0.21. So the other thing that we should note, we haven't gone into the theory of this, and I'll have to for you, is that solids can be oversaturated. For example, crystalline minerals are less likely to form than the kind of metastable or amorphous phases, and we can see that this solution is in fact undersaturated with respect to amorphous aluminium hydroxide. So it's probable that a mineral like boehmite would form too slowly to be relevant anyway, given the seasonal nature of the wetland. So perhaps we don't need to worry too much about oversaturation with aluminium, but there may be some other elements where oversaturation is occurring. So chromium, possibly, yes, oversaturated with respect to a couple of chromic or chromium 3+ phases. But again, if we switch back to our spreadsheet, we notice that we only had total chromium values from our grab sample, meaning that the actual chromium concentration in the dissolved phase, all species, were probably less than that. So we might be able to get away with ignoring that too. We'll scroll down. So here's another crystalline aluminium phase, which unlikely to form during timescales, but here's something that we probably should be concerned about, that we're getting a number of iron phases, which it's suggesting that are oversaturated, and quite significantly oversaturated, and more importantly, a fairly amorphous iron phase that is oversaturated. And again, that may relate to iron values being quite high, because we've got them from our grab sample, and so yes, iron total here was 2.6 milligrams per litre, which is pretty high. Obviously iron in solution not measurable if we look back at the original WI database, so we might need to do something about that. We can have a look at that in a minute. So again, another iron mineral, goethite, appearing to be oversaturated, hematite as well, hercinite, a mixed iron aluminium oxide. So again, and another one here. So look, if you go through, and if there are any others, so that this is interesting. There seems to be a lead phase, which plum gumite or plumbogumite often called, which may be forming as well. So we go back to our spreadsheet and note that lead in fact was a solution value. So maybe there is something odd going on there. Now the something odd we will have to deal with, and then there's a shortcoming of our solution, I think, that we will need to cope with, and we'll deal with that in a minute. Okay, there aren't any zinc phases that I can see which are oversaturated in the solution, so it's probable that the zinc numbers are okay. So possible something happening with lead, especially when we look at pyromorphate, which admittedly is a fairly complex mineral, and it depends on phosphorus, the phosphate concentration, and in our spreadsheet we actually don't have a good value for phosphate concentration. We've only got total P, so again we might want to do something about that. In fact, plum gumite is in the same category, and it also contains aluminium. So look, they're both fairly complex minerals, which may mean that the kinetics are too slow for us to worry about, but it may be worthwhile playing around with that. Alright, so what can we do about that? We've got some output, and of course you can save that. We can save our output as, in fact, it is already saved. So, next thing would be to go back to the input. We can edit these things if we open up the window there, and we can edit our solution. That's what I'm going to do for starters, because there was one thing that we didn't put in, which we did have data for, and that's dissolved oxygen. And we know from our spreadsheet that DO in milligrams per litre was relatively high value, so probably quite oxygen saturated, so maybe our redox value is wrong. Okay, so we will pop oxygen in. So I forgot the value, 11.35. We can pop that in as our 11.35 milligrams per litre, our default units. And we could rerun that, but let's general, so redox, yes, we can select redox on the basis of a particular redox couple, and the one I think I'll use is the oxide oxygen redox couple. So with high dissolved oxygen we should be able to set that, and we'll see what happens there. Alright, so now we have a slightly more perhaps realistic view of the way things are going, so we'll have a look at what happens to our saturation indices now, and so on. Right, so I can run that, start. Okay, do I want to replace the output file? Yeah. Do I want to replace the input file? Yes, I do. Okay, so there it goes. And it ran error free, so we don't need to do anything more about that. We can go back and have a look at the output. Alright, so before we get to, we've got 11 iterations to get us there. Alright, so there are all our saturation indices, and does it change anything? So let's go and have a look first of all at our iron minerals. Ferrihydrite was at issue, and it doesn't seem to have changed ferrihydrite. Let's see what it did to our redox potential in our final solution. Okay, so it's giving us a slightly higher, more oxidizing PE on the basis of the high dissolved oxygen, so that's interesting. But hasn't changed some of our saturation indices. Okay, and there's one more thing we should probably do to our solution, which might make it a little bit more realistic, if you like, and this is going to have to be a guess, unfortunately, because we don't have data on a key parameter, and that is dissolved organic matter. So I would argue, if you like, that dissolved organic matter is very important for trace elements. Now, the Mintech database that we're using does have entries for dissolved organic matter, but it doesn't actually have metal complexation constants for that. So what we're going to do is we're going to pick an organic ligand, and we've got a whole range of them. You can see some of them in here. So there's things like acetate, benzoate, they're what we call monoprotic carboxylic acids. We want something that actually forms complexes well with metals, as we know that natural organic matter does. So we could choose something like citrate, or EDTA is an extreme example, or even something like phthalate, which is a dicarboxylic aromatic acid, or an amino acid like glutamine, or so on. What I'm going to do is, because I know it works, and I know that there is evidence showing that what we call an aliphatic acid nature of natural organic matter is quite reasonable, I'm going to put in some citrate. We don't really know how much to put in because we don't have dissolved organic matter values, so I'm just going to choose a low, what might be realistic value of citrate in our solution, and enter that. Alright, so let's see what that does. We'll save the input file. If we need to get the run button to show, we often need to click here or on in the script window, and then run that. Alright, now I'm going to assume that it's going to run. Everything's going to work. Do I want to replace the output file? Yes, and I'll get rid of that. If we want to check for errors, we can simply go here and have a look, but we quickly find that there aren't any errors to speak of. So we'll go back to our output file and now have a look at the speciation of some key things. Right. So here's our starting solution, the redox couples, blah blah blah, and let's have a look at an element like iron. So for instance, iron, the citrate complex of iron is not so important, mainly because of the high pH, and because therefore most of a strongly hydrolyzing iron element like iron, ferric iron, will be present as hydroxy complexes. But it may be true that for some elements, like nickel, that a sizable proportion of our nickel is in a citrate complex. So for some of the trace elements, organic complexation, here's another example for lead, can be important, and that may remove enough of the free metal ion, this species here, from solution for lead, or free nickel ion for nickel, so that precipitation of their solids is not quite so important. So let's have a look at that. So we have a look at our lead phases. So it hasn't helped us that much. It's reduced our saturation index for lead a little bit, but it hasn't made it negative. So we're still assuming, I guess, that it's possible for a lead phase to precipitate, and because we didn't see a lot of complexation for iron minerals, the saturation indices for those iron minerals probably we're never going to change that much. Alright. One more thing that we ought to probably do. Okay. And this is important because we know that our solutions are in equilibrium with the atmosphere. Now, part of that we've got explicitly because we have in our system, we've got some dissolved oxygen. Alright. But the other thing that we ought to pop in is what we call an equilibrium phase, and I'm going to put in, if I can find it, these are all the solids and gases that are it's possible for our solution to interact with. And I'm looking for something in particular, and that is ERK. Why can I not find it? That's not the one I want. CO2. There we go. Now we're going to adjust the value of its saturation index. Okay, for gases, the number is the log of the partial pressure, and the partial pressure, the log of the partial pressure in the Earth's atmosphere is about minus 3.5 at the moment, and the amount of a large atmosphere in contact with our solution, so we'll leave the amount at 10 moles, so that it doesn't at all get depleted. Alright, so now we've got a new data block in our input file for PhreeqCi, which says equilibrate our solution with carbon dioxide in the gas phase. Right, so save that again, run, yep, dismiss, and let's have a look at the output. So what it will do now is give us slightly more complex output, I think, because it will do a calculation first of all, okay, and then a reaction step. So reacting solution 1 with phase assemblage 1. So when we add a phase in, we need to look at another subsequent block of output where our initial solution is then equilibrated with that phase. And you can see that the computational complexity is getting up there now. We've 25 iterations to arrive at a self-consistent solution here. Now in our list of species we should have this thing C4, or carbonate. Right, so what do we do with that? Well, first of all, we notice that given the pH, that bicarbonate is by far the most abundant species, followed by carbonic acid and then carbonate. We've already seen how all that works, but there'll be a whole lot of other dissolved species, including some metal complexes. Okay, so that's important. The other thing it'll do is potentially allow carbonate minerals to precipitate. So let's have a look at our equilibrium phases. So, but no drama there. Calcite is not going to precipitate. That's good, but there may be some other carbonate minerals for which precipitation is impossible. Is possible. So let's have a look at zinc. No, we're not precipitating a zinc carbonate. Now, what's the name of lead carbonate? Well, siderite's not going to precipitate. Just trying to remember the name. PbCO3. Okay, we've got mixed oxide carbonates. Litharge, is it? No, that's lead oxide. When in doubt, search. Okay, sericite. Some of you no doubt knew that, not a problem. Alright, so probably our carbonate minerals are not causing precipitation. They're probably also not forming carbonate complexes to the extent where we're significantly changing saturation indices for key solids. So again, ferrihydrite there. So the next thing we would do, probably, is because we don't have good data for soluble iron, I'm going to actually make that 0, keep iron in there, but edit my equilibrium phases. So I'm going to find the data block in the graphic window and add in something else. And I'm going to go looking for ferrihydrite. I'm going to add that in. The saturation index at which it will precipitate, we're going to assume 0, that true equilibrium will be attained, and it's the thermodynamic data are good. We'll just put a little bit of it in there and see how we go with that. Alright, so again, save our input file, run. Alright, and scroll down right to the bottom, because that's where we know we'll find our good saturation indices. So what we should look for first of all is ferrihydrite. And we now see that the saturation index is exactly 0, meaning our solution is in equilibrium with ferrihydrite, and therefore the iron concentrations should reflect that. So we had an iron concentration originally of 2.6 milligrams per litre. So what we need to do is then scroll up to iron, and we're predicting a ferric iron concentration of 3.8 by 10 to the minus 8 moles per litre, which I believe, without doing the calculation, is significantly greater, less than 2.6 grams per litre. In fact, let's go to Excel and do the calculation. Alright, so we've got a value here, which we can pop in. Moles, just to make sure that we know what we're talking about. And the atomic mass of iron is about 55.85. Actually, I do remember this. It's a bit geeky, but I remember the atomic weights of a lot of elements. Yeah, tells you something about my personality. The units of that, of course, are grams per mole. So, therefore, if we multiply these two together, and in fact, this should be times 1,000, and that means the units then become milligrams per mole, right? Happy with that? And if we multiply those two together, it gives milligrams per litre because the moles cancel out. So there we go. So that number is much smaller, right? So if we express it as a number, give it a few decimal places, we should have got a number of 0.0021, give or take, our actual number, if in fact ferrihydrite is controlling solubility. Compare that with the number for iron total. So what that probably means is that when the analysis is done, we're not filtering out enough finely colloidal material, which is going through the filter, so there's some iron-bearing solids in there, probably minerals like ferrihydrite, which are actually going through our analytical machine.